Okay, so we're going to spend 2 days on this, and I think we're going to do it a lot like yesterday, or the last section, where we're going to talk about X and then we're going to talk about Y separately. Okay, so we're going to rotate in the same direction all day today. Okay, make it. Okay, so this is what's going to happen, and you don't need to write anything down until I tell you to, okay? So you can kind of relax for a little bit and just participate with me, if you will. What we're going to do, and here's some nice pictures, we are going to take a region. We're going to take a region, and we're going to rotate it about some sort of line, vertical or horizontal, to get some sort of three-dimensional figure. Okay? Some of them are going to be solid. Some of them might have a gap in the middle somewhere. All right? But our goal for the next 2 days is to find the volume of these. Okay? So we are going to have to draw our regions and kind of imagine what they're going to look like as they rotate around a line. Okay, and then go from there. So, bear with me here. We have a region where we have f of x and g of x. They meet. We have f of x is our upper function, g of x is our lower function. Okay? What is going to happen when we rotate this around the x-axis? I want you to try to imagine it before I show you what it looks like. We're going to rotate it around the x-axis. Are you ready? Yeah. What does it make you think of?
Coliseum.
It kind of looks like some sort of arena, right? Where it kind of like lifts it down. Okay, that's not what you were thinking. I'm getting giggles. I was making.
It's like a bowl of popcorn.
Bowl of cereal, bowl of popcorn. Okay. Well, and we can see that since it's flat up against the y-axis, it'd be like flat on that side, right? And then it like kind of like caves in, right? Okay. Just like our area, we're going to break it up into rectangles, but we're going to take these rectangles and we're going to rotate them around. Now, you can see that when we create our picture, though, we're going to have like a gap in between, so we are going to have to account for that, okay? But we're going to take these rectangles, we're going to split it up into rectangles, and we're going to rotate those rectangles around, okay? Now, if we take a picture like this and we rotate rectangles around, we are going to get what looks like either a disc or a washer. A disc would be like a solid flat cylinder, okay? A washer is when we have like that gap in the middle, okay? So that red one was a washer, or excuse me, a disc, and then these all look like washers, okay? So what we're going to have to do is we're going to have to imagine those infinitely thin rectangles, rotating them around as infinitely thin discs or washers, and find the volume of those and add them together. That's what we're going to have to do. Now, do you know how to find the volume of a disc? No? Okay, so the volume of the disc is just pi r squared h, right? You still don't have to write this down. You still don't have to write, okay, Ashley has to write this down. The volume of a disc is pi r squared h. Now, how do we find the volume of a washer? Let's think about it.
Subtract the volume that would be inside.
Okay, we have to subtract out the whole, right? Which is also a infinitely thin cylinder, okay? So what we're working with here is pi pi r squared of the big one, pi r squared h of the outer minus pi r squared h of the inner. And so I can write that as pi r squared minus r squared h because the heights are having to be the same, right? Okay. So now we're going to think of this in terms of infinitely thin rectangles that we are rotating around to make discs. Okay. What's going to happen is that, let's see if I can make this. Basically, the radius of our outer function is the top function. The radius of that hole is going to be how far away that smaller function is from the axis, okay? So what's going to happen is our radii become our two functions, our top function squared minus our bottom function squared. And then when we think about these rectangles being infinitely thin, remember how I had you draw those rectangles? Their thickness is dx, okay? Well, the thickness, that's the height of all of those cylinders, right? So delta x becomes our height. Okay, well now we want to add all of these together. Okay, well we use integration to add all the areas together, right? All of the infinitely thin rectangles, that's how we added them all together, integrating. Okay, well that's what we're going to do here. We are going to sum all of these up together, and as we get those, that thickness to be smaller and smaller and smaller, we're essentially talking about an integral. This is what I need you to write down. Okay, this is the disk washer method. For volume of revolution. I usually just call you can call it both disk and washer method. Really, it's the disk method if there is not a gap, because there's no hole to subtract out. Okay, it is the washer method when you truly have some gap in the middle, like the picture that we said. Okay, so if it's the disk method, you're not going to have a hole to subtract out. If you have a washer, you have that key of X to subtract out. Okay? Now, you need to know how to set up a problem. You don't necessarily need to know how to come up with a formula like I just did, but I like you to actually know what the mathematics is behind the formula and where it's coming from. Okay? So essentially, we have the integral of pi r squared minus r squared h. Okay? So we're going to do two examples where we are rotating around the x-axis, okay? Just like we did the previous 2 days, you need to draw a picture, and the most important thing in your picture is that rectangle, and I'll show you why. All right? So go ahead and write down any information you need to about this example right here. go ahead and start working on a picture for me. Okay, so we have y equals x. I have my line with slope 1 going through the origin. I have my parabola shifted right 1, up 1. Okay, but then it's also bounded by x equals 0, this right here. So the region that we're talking about, I'm going to have my highlighter in PowerPoint. This is the region that we're talking about right here. Okay, so really if it were me, I would go back and I would erase all of this other garbage because it's not necessary and it's just crowding up my picture. Okay, you don't have to, but I like to get rid of it. It's in the way. Okay, now we are rotating about the x-axis. So I need you to draw me a circular arrow indicating that you are rotating about the x-axis. Then I need you to draw a rectangle. Okay, right now we only know how to rotate about a horizontal axis. And we only know how to find the volumes of discs and washers. So if we draw a vertical rectangle with thickness dx, we know that when we rotate around the x-axis, we're going to get these washers. Okay, you can imagine rotating it around and we have these thin washers to rotate. Okay. All right. Now, this isn't necessary, but if it helps you, you can even draw in kind of what it's going to look like, right, using some symmetry. It's going to kind of look like an inverted volcano. Okay. All right. That part's not necessary. The green part, that with the rectangle and the arrow are all necessary in your picture. Like you're getting points for drawing your picture. Okay. So now let's set this up. We know that since we have washers that we're rotating around, that we're finding the volume of, we need pi times the integral of r squared minus r squared h, which is our thickness. Okay, now we just need to decide what are our radii. Okay, so our largest radius is here, our top function, which is what? Okay. Okay. And then our inner function, or our inner radius, is just whatever our bottom function is. Last piece of this, where are we integrating from? Okay. Well, since we're integrating with respect to x, we need to look left to right. Our picture begins where on the left? 0. And our picture ends where on the right? 1. Now, if I had you integrate this by hand, would you be happy?
No.
I wouldn't either. That's a lot of tedious algebra before we can even integrate. So this is what I'm going to have you do. Go ahead and get out your calculator. And what I'd like you to do is use the math9 command, but do not multiply by pi yet. Okay. Do the math9 command without the pi. Okay. Are you getting something? What? What? Oh, that's so boring.
1.5.
Unit square in here. Unit square this radius.
Oh,
You do the same thing?
yeah.
Unit square then. Okay, 1.53. Can you change that to a fraction for me, please?
23/15.
What is it?
23/15.
Okay. So April is getting 23/15 for the integral without the pi. So then we can just, hey, multiply by the pi. That is how I would want you to get your answer if you're using your calculator. Now let's talk about a couple of things with this problem. If this were a non-calculator problem, I would not make you find the answer. I would just say set it up. If this were a calculator problem, then obviously you could use the math9 command. But this is how I would want your answer. The only time I want you to give me a decimal is maybe if you get an irrational integral, like you get a decimal that cannot be changed into a fraction, then multiply by pi and give me a decimal. All right? Please don't give me a decimal 5.993 pi. No. Just take the 5.993 blah, 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 and multiply it by pi and then give me a decimal. People do that every year, and it just, it's like the sound of styrofoam, like it just, yes, like that. Okay, next example. This is going to be a full-out non-calculator problem. Find the volume of a solid formed by the region y equals radical x from 1 to 4 about the x-axis. Square root of x. Best function to graph, right? Maybe not best, but nice. So we have the square root of x, but only from 1 to 4. I don't really care about this other stuff, right? We're going to rotate it about the x-axis. The only way we know how to do it is, there's something funky with my board, I don't know what's going on, but that is a vertical rectangle. And that doesn't look like it. Okay, with thickness dx. And I want you to imagine that vertical rectangle. Like, look at that vertical rectangle and imagine it rotating it around the x-axis. What are you picturing? You're picturing a disc, like a plate, right? You're picturing a disc. Okay, good. If you want to imagine what it would look like, right, we can mirror this. And basically we have kind of like a cup, right? Sounds like a cup. I think Amy is hungry for a bowl of cereal. Oh, actually, it's hungry for a bowl of cereal. Okay. So let's talk about the volume. What's different about this problem compared to the first one?
No subtraction.
There's no hole, right? So all we have to worry about is the big radius, because the small radius is, well, nothing. All right? So we have pi times our integral, radius squared minus 0 squared dx. And what is our radius? F of x. So radical x. And radical x squared, that makes for a pretty nice integral. Okay, well, what are our limits of integration? Yeah, that's nice. They give it to us, right? Okay, I'm going to give you about a minute to get through this integration. If you have a question about the setup, then you can catch me as we're working here. Check with your neighbor to make sure you're getting the same thing. You're getting there.
Why,
I would definitely wait for the pi until the very end. I'm seeing a lot of 15 over 2 pi. You have to subtract, right? 8 minus half. Okay. So we get 15 halves times pi. All right. Now, this is nice, right? It hasn't been too bad. We're just rotating around the x-axis. What happens if the x-axis is no longer our axis of rotation? What if I give you a horizontal line that is not 0? That changes the game a little bit, doesn't it? Don't panic. It shall be fine. But we're going to talk about the region bounded by x squared and x rotated about the line y equals 2. So write down the information that you need. The region of f of x equals x squared, g of x equals x, rotated around y equals 2. So for our picture, we have a line and a parabola. We can already tell where they're going to intersect, right? Which two coordinates are they intersecting at?
0, 0,
0, 0, and 1, 1. Here's our line. Here's our parabola, right? Okay. If you draw the rest of the graph, that's fine. I really try to erase the rest of the graph so I can focus on that region. Okay. Now, we want to rotate about the line y equals 2. Okay. So our axis of rotation is now above our rectangle with thickness dx. Okay, so we're going to have to be a little careful here. We still need outer radius minus inner radius, but we're really going to have to think about which radius is bigger, which radius is smaller, and we're still going to have to consider top minus bottom. Okay, so first of all, is everyone okay with the picture? Okay, we're going to get kind of like a donut, right? Maybe this, a bagel that's been cut in half, because it's going to be kind of, well, not really, it's not going to be flat. We're going to call it a donut. It's a weird donut, okay? So we have these vertical rectangles. Please imagine, okay, they're pretty small, but they're rotating about y equals 2, so we're going to have these really small, but right, like a big hole, right? We're going to have a really big gap, but we're going to have these washers, right? Okay. So pi times the integral outer radius squared minus inner radius squared pi. Do you have a question or an idea?
Would the outer radius be the functions minus each other, and then the inner radius be the 2?
It is actually not. Okay, this is what we have to think about. Okay? The functions subtracting each other really mean nothing right now. Okay? Technically, from the axis of rotation to the curve, that would be the whole, right? From the axis of rotation to the outside of our rectangle, that would be the bigger radius. Okay? So instead of concentrating here on the rectangle top minus bottom, we need to think about where our rectangle is in relation to the axis of rotation. Okay? Since we are talking about an axis of rotation that is above our curve, it's higher, we're going to have to take that 2 and subtract the bottom function for our big radius. So here is 2 minus all the way our outer radius is ending at this x squared. Okay? So 2 minus x squared, that is our outer radius. Whereas our inner radius is going to go from the top of the rectangle all the way to the axis of rotation. But since the axis of rotation is on top, we're still going to do that top minus bottom, 2 minus x. Okay? So I want you to focus on the axis of rotation to the top of the rectangle, axis of rotation to the bottom of the rectangle, and whichever one of those is bigger, that needs to come first for your big radius. We need to talk through that again.
Why is it 2 minus x again?
It's 2 minus x, so here, axis of rotation to the top of our rectangle, that would be the shorter radius, that's our gap. And since 2 is on top, we still have to do top minus bottom here. So 2 minus our line x. Does that make sense? Okay, so our outer radius, we do 2 minus the bottom of our rectangle, x squared. For our inner radius, 2 minus the top of our rectangle, x. That is one, probably wouldn't make you do by hand. That would be very nice. let's do the same region. I should have written that. I'm gonna rewrite it over here. Okay, let's take the same region but rotate it about something different. Okay, this time we're going to rotate about y equals, let's say, -1. Okay. So our region is going to be the same, except now we're going to rotate about the line y equals -1. Okay. So now let's talk about the differences here. Okay. What I want you to do is at your table, talk about, like, draw out where is our outer radius, where is our inner radius. Either describe it or point it out on your picture.
Well, you take top minus bottom. So your outer radius is going to be like x is the top, and then y equals -1 is like the bottom. So it'd be x minus -1.
You switch them because now
And the square is closer to that. And the other one would be
Okay. We still need to keep in mind that we have to do top minus bottom. Okay? So now that our axis of rotation is underneath of our curve, we're going to be talking about the rectangle first and then our axis of rotation. Okay? So, April, where did you guys describe the outer radius?
we said it was g of x.
Okay, so we have to say, okay, since now we're underneath, the top of our rectangle is furthest away. Do you agree? So from the top of the rectangle all the way to the axis of rotation, that's our outer radius. Okay, and we still have to keep in mind the top minus bottom. So we would write x, that's our function, minus -1. Okay, and then the only thing that's left, our inner radius would be the bottom of the rectangle to the axis of rotation. Keeping in mind the top minus bottom, we are going to have the x squared minus -1. Questions about the difference between those two? Go ahead and get this stopped.